the autoionization of water. Okay? Like I said, KQ for the reaction, for this reaction is known as KW, and this particular reaction is this one right here. Okay? In water, okay, even if you have pure, ultra pure water, it's not all going to be just water molecules. So at any given instant in ultra pure water, a very, very tiny fraction of your water molecules are actually in the form of hydronium and hydroxide ion. And the way these are formed, okay, let's say you have two water molecules, is a proton can hop from one molecule to another. In fact, protons do that a lot in water. They hop from one molecule or ion to another. So as long as they find a lone pair that they can latch onto, they can hop to it. Okay, so when this happens, when a proton, H plus, transfers from water to another water molecule, you get hydroxides left behind, right? This is going to be your hydroxide that's left behind, and you make hydronium ion. So H plus H2O will give you hydronium ion. So this reaction right here occurs to a very small extent, but it does occur. It's significant, and it's significant enough to make a big impact in a lot of systems, especially living systems. So this is the what's known as the autoionization. It's autoionization because it just happens in water automatically in a way. And you can abbreviate this by just writing it as H2O liquid yields H plus aqueous plus hydroxide. So when we say H plus aqueous, what we really mean is hydronium ions. Okay, none of those H pluses are actually by themselves. They're latched onto another water molecule. Some of them may be latched onto two water molecules. Okay, so it might be surrounded by several water molecules. So we're just going to abbreviate that as H plus. Okay, so Kw is H3O plus times OH, concentration of hydronium ion, or more precisely, the activity of hydronium times the activity of hydroxide. Or we can write that as activity of H plus times the activity of hydroxide. Now, this is a value you have to memorize. At 25 degrees Celsius, the value of Kw is 1.00 times 10 to the negative 14. So if you have pure water, what do you think H plus and hydroxide is going to be at 25 degrees? Let's look at this reaction again. Oops. Let me write that as H plus plus hydroxide, and Kw is 1.00 times 10 to the negative 14. 10 to the negative 14, is that a very big number or a very small number? Very small number. So you can say you're going to have just trace amounts of hydrogen and hydroxide ions in water, in pure water, right? And if you're going to lose X moles of water, then you get, if you make X moles of H plus, then you're also going to make X moles of hydroxide. So in pure water, you're always going to have equal amounts of hydrogen ions and hydroxide ions. So how would we solve for X here? So H plus and hydroxide would be the same, right? And so let's just say it's equal to X. What's the expression for Kw? Equilibrium constant is activities of products over activities of reactants. So it's going to be H plus times hydroxide divided by activity of water is 1, right? So that's just going to be X squared over 1. So how do we solve for X? 1.00 times 10 to the negative 14 equals X squared. So that means X must be equal to 1.00 times 10 to the negative 7. So that is the concentration of H plus and hydroxide in pure water. Okay, so H plus times hydroxide, okay, this would be 1. H plus and hydroxide will both be 1 times 10 to the negative 7. Now, if you were to add things to water, contaminate your water, the solids that you add could alter the H plus and the hydroxide concentration. You could be adding something that would give you more, that would produce H plus in water. You call that an acid. You can add something that would produce hydroxide in water. You can call that a base, right? But the product of H plus times hydroxide must be a constant. That's equal to Kw. So these two will always be equal to a constant. What does that mean? If H plus times hydroxide is a constant, okay, it's equal to a constant. If H plus goes up, what must happen to hydroxide in order for the product to remain constant? Let's go down. Like if I multiply this by 2, I have to divide this by 2 in order for the product to remain the same, right? So if this was 2 times 10 to the negative 7, okay, then this is going to be 0.5 times 10 to the negative 7 in order for the answer to still be 10 to the negative 14, right? So if one goes up, the other goes down, right? That's you've seen this relationship lots of times already. Whenever the product of two things is a constant, we say they are inversely proportional. Remember Boyle's law? Pressure times volume equals constant. Pressure goes up, volume goes down. Same idea here. Okay? So anytime you alter the concentration of H plus and hydroxide, you can still figure out what the concentration of the other one is. So calculate hydroxide if H plus is 2.50 times 10 to the negative 4 moles per liter. Now, unless otherwise specified, when we talk about these reactions, always you can assume it's at room temperature of 298 Kelvin, okay, or to be more precise, 298.15 Kelvin, since we're dealing with 25 degrees Celsius, okay? All right, so if this is the case, what's my hydroxide? How do I calculate hydroxide? I know H plus times hydroxide equals 1.00 times 10 to the negative 14. How do I solve for hydroxide? Divide both sides by H plus, right? So hydroxide is equal to 1.00 times 10 to the negative 14 divided by 2.50 times 10 to the negative 4. This one would be 1. One point zero times 10 to the negative 14 divided by 2.5 times 10 to the negative 4. And make that scientific notation. That's 4 times 10 to the negative 11. How many sig figs? 3 sig figs. Okay? So, what's higher in concentration here, H plus or hydroxide? 10 to the negative 4 versus 10 to the negative 11. Which one's higher? More H plus in this particular solution. Okay, this is greater than 10 to the negative 7, right? And this is less than 10 to the negative 7. Okay, and so when we have a solution like that where the hydronium ion concentration or H plus concentration is greater than 10 to the negative 7, you say you have an acidic solution.